Good morning, friends. Now, in previous lecture, we have discussed about the chemical reactions of alkyl halide. In that lecture, we have studied what is meant by or how to prepare alkyl halides, how to prepare alkyl nitride, how to prepare alkyl isonitride. Along with that, we have also seen how to prepare nitroalkanes and alkyl nitride. Now, moving towards our this lecture, we have in this lecture particularly we have to see what is ether formation, that is Williamson's ether synthesis. Along with that, we have to also focus on elimination reaction. What is meant by elimination reaction, or how will be alkyl will be formed? How will alkyl will be formed by alkyl halides? In Williamson's ether synthesis, when alkyl halide is treated with sodium alkoxide, we will obtain ether as a product. And now, on the basis of, we know that what is meant by ether and its types. Now, the ether which is obtained in this synthesis is either symmetrical ether or unsymmetrical ether. Now, when alkyl halide is treated with sodium alkoxide, which is used as a nucleophile here, as this oxygen atom carries negative charge, we obtain symmetrical or unsymmetrical ether. This formation of symmetrical or unsymmetrical ether depends upon which alkyl halide we use, along with which alkoxide ion also used. If we use the alkyl group in alkyl halide and alkyl group from this alkoxide ion is same, then we will obtain symmetrical ether as a product. If we use alkyl group from alkyl halide and alkyl group of this sodium alkoxide, these groups are different. If these groups are different, then we will obtain unsymmetrical ether as a product. For example, moving towards our reaction, firstly we have to see how these alkoxide ions are formed. When alcohol molecule, that is ROH, is treated with sodium metal, we will obtain this alkoxide ion. Now, this alkoxide ion, which is recently formed here, we have to use as a base or nucleophile in our Williamson's ether synthesis. Now, when this C2H5Cl is treated with C2H5 ONA, that is when this ethyl chloride is treated with what? Is treated with ethoxide ion. obtain C2H5O, C2H5, that is diethyl ether as a product. Now, I have already told you that when we use this alkyl group and alkyl group from this alkoxide ion, if both these groups are same, we will obtain symmetrical ether as a product. In symmetrical ether, both the alkyl groups present on both sides of this oxygen atom are same. While in case of unsymmetrical ether, these two alkyl groups will be different. Now we have to take an example of the formation of unsymmetrical ether. When this methyl bromide is treated with ethyl alkoxide or ethoxide, we will obtain methyl ether methyl ether as a product. Look at this product. We observe here that both the alkyl groups on this and this side of this oxygen atom are different. Hence, it is unsymmetrical ether. Now, there is one also reaction which is nothing but elimination reaction. This elimination reaction is also called as beta elimination, and along with that, in this reaction there is a removal of hydrogen atom and halogen atom from alkyl halide, and we know that removal means D, and here in this case hydrogen and halogen atoms are removed. That's why this elimination reaction is also called as dehydrohalogenation reaction. That in that case, the hydrogen atom and halogen atom which will be eliminated is present on For example, in this case, we know that the halogen atom present on the carbon atom, that carbon atom is called as alpha carbon atom. The carbon atom which bears halogen atom called as alpha carbon atom, and next to this alpha carbon atom, this carbon atom is nothing but beta carbon atom. In case of elimination reaction, the halogen atom from alpha carbon atom and hydrogen atom from this beta carbon atom will be eliminated. That's why it is also called as beta elimination. I have explained you about that. This is beta elimination reaction. Now, in many elimination reactions, we obtain mixture of products. This is because of, as if that alkyl halide or if the number of beta hydrogen atoms in alkyl halide increases with respect to this halogen atom, the formation of mixture of product will also be increases. So we have to see each and every aspect of. Now we have to see each and every aspect of this elimination reaction. Now, in case of substitution reaction, we use alcoholic, we use aqueous KOH, whereas in case of this elimination reaction, we use bases like alcoholic KOH, alcoholic NaOH, or alkoxide ions. Now, when alkyl halide is treated with or heated with alcoholic KOH or alcoholic NaOH, we will obtain alkene as a product. That alkene which will be obtained by this elimination reaction, the formation of that alkene depends upon what? It depends upon the presence of beta hydrogen atoms. If there are two or more than two beta hydrogen atoms present in any example, we will obtain mixture of product. Whereas if any molecule or any alkyl halide carries only one beta hydrogen atom with respect to that halogen atom, then we will obtain only one product as only one product. Now, up till now, we have seen the concept arises in elimination reaction. In this elimination reaction, we have to take some examples to understand which concept we actually study in practical manner. When this N-propyl chloride is treated with alcoholic KOH, here we know that this KOH acts as the OH negative present in this alcoholic KOH acts as a nucleophile, and this nucleophile here in this example will prefer to attack on the beta hydrogen atom. Now, due to its higher concentration, and this beta hydrogen atom generates, or this beta hydrogen atom which will be eliminated is eliminated with this halogen atom to form this 1-propene as a product. Now, look at this example with respect to this halogen atom. We know that the halogen atom, the carbon atom which carries this halogen atom is alpha carbon atom, and next to alpha carbon atom, this carbon atom is beta carbon atom. This is beta carbon atom, and beta carbon atom carries a beta hydrogen atom. Now, this OH negative present in this alcoholic KOH acts like this proton, and the electrons present in this bond goes to these two carbon atoms with the elimination of this leaving group here, that is chlorine atom. In this way, we will obtain this 1-propene as a product. Now, we have also know that if, and in that case, there is only one beta hydrogen atom. There is only one beta hydrogen atom with respect to this chlorine. That's why we will obtain only one product here. Now, our second example. This is 2-bromobutane. Now, when this 2-bromobutane is treated with alcoholic KOH, here in that case, we know that the carbon atom on which this halogen atom is present is alpha carbon atom, and next to this alpha carbon atom, we have 2 beta carbon atoms here. Now, this OH negative in this case will abstract this beta hydrogen atom to form one product, whereas in another case, this OH negative subsequently abstract this beta hydrogen atom also to form another product. These 2 products will be formed. Now, we have to discuss out of these 2. No doubt, these 2 products will be formed, but the amount of this product formation is not equal. Obviously, out of these 2, one will be obtained in major extent, whereas the another will be obtained in minor extent. Now, we have to understand that concept, we have to know about what is meant by S.Y.B.Sc rule and what is meant by Hopman rule. Now here I will tell you that this more substituted alkane is obviously always formed in major extent, and this will be formed in minor extent. To understand its formation of mixture of product, we have to know about what is meant by S.Y.B.Sc rule and what is meant by Hopman rule. Now, move towards our next topic of this lecture, that is S.Y.B.Sc rule. Now, we know that to understand the formation of mixture of product in elimination reaction, we have to know about 2 rules. That is, out of these 2 rules, one is S.Y.B.Sc rule and Hopman rule. Hopman rule is also called as Hopman elimination. Now, generally, in presence of small bases and small leaving group, we will obtain more substituted alkene as a major product. Now, this S.Y.B.Sc rule states that in an elimination reaction, more substituted alkene will be formed as a major product. It means at simple conditions, if we use small bases which has less steric hindrance or small leaving group which also has small or less steric hindrance, in such cases we will obtain more substituted alkene as a major product. We know that we have taken the previous example. Now we further have to take another example to understand this concept. When this now look at the previous example. When this 2-bromopropane is treated with what? Is treated with alcoholic KOH. We have obtained two products, that is this 2-butene and this 1-butene. Now out of this 2-butene, this alkene is more substituted because the olefinic carbon atom present in this alkene has substituent on both the sides. Now in this case, this is the terminal alkene. Only one carbon of only one olefinic carbon has only one alkyl group. That's why it is less substituted. Now S.Y.B.Sc rule states that this alkene, that is more substituted alkene, will be formed in major extent. Now when this alkene will be formed in major extent? When the leaving group, that is halogen atom in this case, and this base, that is alcoholic KOH, if this leaving group and this base will be used in this reaction is smaller in size, then we will obtain this more substituted alkene as a product. If now the second rule of this elimination reaction, that is Hopman rule, if instead of this product, instead of this major, we have to prepare 1-butene as a major compound, then for that purpose we have to use this leaving group and this base in bulky size. For that purpose, second rule of this elimination reaction we have to study, that is Hopman elimination. In Hopman elimination reaction, we obtain less substituted alkene as a major product. It means it is in case of Hopman elimination reaction, we obtain this less substituted alkene as a major product, and this will be more substituted alkene will be formed in minor extent. Means it is totally opposite to which S.Y.B.Sc rule. We know that in S.Y.B.Sc rule we obtain this as a major compound, whereas this less substituted alkene obtained as a minor compound. Now for that purpose we have to change our leaving group and base from less bulky to bulky. That is, if we increase the steric hindrance and instead of this Br, if we use tosylate OTS, which is the bulky leaving group, and along with this KOH, if we use tertiary butoxide ion, then this, due to its steric hindrance, it cannot be abstract this more substituted beta hydrogen atom. Instead of it, this bulky tertiary butoxide ion prefers to abstract this less crowded beta hydrogen atom to form this 1-butene as a major product, whereas this 2-butene will be obtained as a minor product. This is all about the elimination reaction. Thank you.